So today, our mathematician spotlight is Illya V. Hicks, who is a professor of computational and applied mathematics at Rice University. So he was a math major at Texas State University, where he was on the football team and also aced calculus. So here's this cute picture of him in calculus class, because calculus was so easy. He just reclined and had a great time in calculus, like many of you are doing right now. So there you go. And now he is grown up, and he studies combinatorial optimization, graph theory, and integer programming. So graph theory, a graph is like you have a bunch of things called nodes, and you connect them with edges in some way. Who knows how they're connected? And then you want to know, I don't know, how they're connected. Maybe you can have double ones. Not clear. Okay, and then you want to know, maybe not. Let's not do that. So you could imagine that this is like a bunch of people, and the connections are if they're friends. So like a social network. Or you could imagine that it is the cells in your body, and they are connected if they, I don't know, if they're connected, if they interact, these cells. Or you could imagine that they are computers, and they're computers that are communicating via the internet. Like you try to go to a website. Some computer has to send you the information from the website. So his research, which is on graph theory and combinatorial optimization and integer programming, has applications to cancer treatments, social networks, and network design. So that's when this graph would be much, much bigger. So if it's just this little graph, it wouldn't be so hard to analyze it. But as you can imagine, if you have cancer treatment, there's millions, billions of cells. Social networks have lots of people in them, and networks of computers have lots of computers. So you need serious math to deal with that sort of thing. All right. So we're getting to the end of the semester. We've learned all our big theorems. And so for the last 2 days, we get to play with them. So today, we'll do a couple examples of Gauss's theorem, where you have to close off a surface. So we'll get really good at closing off surfaces. And then, just so you know what's happening next time, we might go outside, because it's supposed to be cloudy, so it might be a little bit easier to be outside. And we'll do an example that brings together Stokes' theorem and Gauss's theorem. And then I'll just sort of do a summary of the things that we can integrate now as of the end of the course. So that's the plan for what's happening. All right, so let's do it. So for instance, suppose you have this surface, which is 5 faces of a cube, the top 5. So here they are, the unit cube. Can you move that thing? Thank you. So we have there, you have the top 5 faces of the cube, and this is the unit cube. So the origin is there in the back. Here's the x-axis, here's the y-axis, here's the z-axis, and all these things are length 1. So that's your surface, but it's missing the bottom. There's S, and it's oriented outward. Okay? And you wish to compute the flux, or the vector surface integral, of a certain vector field over that. So compute the vector surface integral over your surface of some crazy terrible function, p of xy, some crazy, p of yz, some crazy terrible function, q of xz, and then this nice function 3z dot ds over this surface. That's what you want to do. So let's see. So to compute this, option 1 would be to just do it. Whatever. S has these 5 parts, these 5 faces, but each of them is pretty simple. It's just a square, so easy to parameterize. And then just compute the surface integral. But the two things that might stop you, give you pause, are that S has 5 pieces. So this is going to be a bit of a technical calculation. It's going to have a lot of parts, tedious. And we don't know P or Q, those first functions in our vector field. And we're perhaps told that they're a mess. So if we could avoid using them, it would be great. In particular, we'd love to just only be able to only use the divergence of this vector field. So if this is our vector field F, check it out. The divergence of F is the derivative of the first thing with respect to x plus the derivative of the second part with respect to y plus the derivative of the third thing with respect to z. These two first parts cancel out. So we'd love to be able to use a divergence. So we'd love to be able to use Gauss's theorem. So we want use Gauss's theorem, which is also called the divergence theorem, because it's all about the divergence. But Gauss's theorem is for a closed surface. Gauss's theorem says that if S is closed, the integral of f dot ds over S is equal to the triple integral over the interior of the divergence of f dv, but only if S is closed, now you probably can't see this, and oriented out. So S has to be a closed surface, meaning it doesn't have any boundary. And this thing has boundary. So the idea that we can do is, how about we close off S so it becomes a closed surface? So our idea is to close off S, apply Gauss's theorem, and then subtract off the flux over the added part. So let's try it. So the idea would be that by Gauss's theorem, the double integral over the over some closed surface of f dot ds is equal to the triple integral over the interior of divergence of f dv, as long as the surface here is closed. So I haven't written it here yet because we don't have a closed surface. Let's close it. So in order to close this cube, we could add any other surface. But maybe the simplest one, any other surface that has the boundary, this bottom square, like edge square. So let's add the simplest one, which would be just the bottom face of the cube. So let's add in this surface S1. So then this is going to be S plus S1. Now, in order for Gauss's theorem to work, so Gauss's theorem says if S is closed and oriented out, this thing is true, where E is the region inside S. So we need the entirety of this closed surface to be oriented out. So what do you think? So for S1, should we use the normal vector going up or the normal vector going down? Yeah, down. Why do you think so?
Isn't it pointing outwards? So, I don't know, pointing down and not up, because if it was up, then it would be inwards.
Yeah, right. Yeah, exactly. So the surface S is oriented outwards. So the surface S1 needs to also be oriented outwards. And if it was pointed up, then it would be oriented inwards. So this is different from what we've been doing, where we said surface integrals were independent of surface as long as you kept the same boundary. Then we were like we wanted to turn S into a different surface, and then we would want things to sort of be pointing in the same direction. But here we're trying to make a surface where all the orientation is the same way. So we want S1 is oriented out, so it has normal vector 0, 0, minus 1, because it just goes directly down. Okay. So by Gauss's theorem, now that we have a closed surface oriented out, we can use this theorem. And then the flux over the whole thing, the white part S plus the pink part S1, is equal to the flux of each part added together. So this is the flux over S of f dot ds plus the flux over S1 of f dot ds. And Gauss's theorem says that's equal to the triple integral over the region inside of divergence of f dv. So the part that we want is this part here. This is what we want. So we can solve for that. We can solve for that by saying the flux over f of f dot ds is equal to the triple scalar integral over E of the divergence of f dv minus this part. So just move this part over to the other side of the equation. So minus the double integral over S1 of f dot ds. So this is what we'll do. We'll compute what this would be the flux over the entire surface, and then we'll subtract off the flux over the bottom to give us the flux over the surface that we want. So let's do it. So we've got two parts, this first part and this second part. So let's compute them both. So for this first part, we want to compute the triple integral over E, which is the interior of the cube, the solid cube, of the divergence of f dv. Okay, we kind of talked about the divergence a little bit, but let's compute it again. So this is the triple integral over E of divergence of f. So derivative of the first part with respect to x, 0. Derivative of the second part with respect to y, 0, because these are just P is purely a function of y and z. There are no x's in it at all, so derivative with respect to x is 0. Similarly for q, it hasn't got any y's in it at all, so derivative with respect to y is 0. And then derivative of the last part with respect to z is 3. So the divergence of f is 3 dv. So 3 is a constant, we can pull it out. This is 3 times the triple integral over E of dv, and then that's just 3 times the volume of E. So 3 times the volume of E, and E is a unit cube, 1 by 1 by 1, so its volume is 1. So this is 3 times 1, which is 3. So now, yeah, that's the first part we wanted. And then for the second part, we need to find the double integral over that bottom square of f dot ds. Okay, well, one way to do it would be to parameterize the bottom. But let's see if it might work out easily if we just use the unit normal vector. So that's the double integral over the bottom surface of f dot unit normal vector ds, which is the double integral over S1 of f. F is P, Q, 3z. N is, let's see, we figured out the normal vector that this thing is oriented out, so the normal vector goes down. The normal vector is 0, 0, negative 1. So this is 0, 0, negative 1 ds. And so when you take the dot product, P whatever it is times 0 is 0, Q whatever it is times 0 is 0. So we get the double integral over S1 of negative 3z ds. Okay? Now if we wanted to, we could set this up as a double integral as x goes from 0 to 1 and y goes from 0 to 1 of this function dx dy. But z, there are no z's in that at all. So it looks like maybe z is constant on our region. So on our region, actually, our little piece is sitting in the xy plane. So z is 0. So z is 0 on S1. So this is the double integral over S1 of negative 3 times 0, which is 0 ds, which is 0. So now we can finish our calculation. We found the two pieces we wanted. The flux over the entire surface, which we got from doing the triple integral over the interior, was 3. And then the flux over the thing that we added, that bottom surface, was 0. So the flux over the surface that we want is 3 minus 0, which is just 3. Questions or ideas? Yeah.
Can we make an argument geometrically that the flux across S1 has to be 0 because the P and Q terms won't affect it because they're like perpendicular to surface, and then the Z term is just defined as 0?
Yeah, we could make a geometric argument without doing any algebra at all. So that P. Oh yeah, okay. So these two are in the xy plane. Okay, so they're just going to be perpendicular to the normal vector to the surface, so that shouldn't make any difference. And then 3z, well, z is always 0. Yeah, nice. So we can argue geometrically without doing any calculations. You mean just for the bottom face?
Yeah.
Yeah, just for the bottom face. Okay. Yeah. Yeah. You might be able to make a geometric argument for the other faces, but it might take you longer than doing this calculation. Yeah, good question. Other questions or ideas? Okay. Perhaps this is a good time for a class photo. I think I'll stand on this side. Okay. Let's see if we can get all of you in it. Great. Probably not, but let's see. Okay, we have a choice between the two of you. So, okay, would you be willing to move back into the different chair? Okay, super. Thank you. Ah, so good. Okay, ready? Not quite. So good. Okay, ready? Here we go. 1, 2, 3. Boom. Ready? Once more, just in case. 1, 2, 3. Boom. Okay, thank you. Good. I'll try to remember to send them to you, but usually I forget, so I just get to keep them. Okay. Good. So, let's go on. Good. There, we did that. So for the rest of the time, we'll just do 2 more examples of other things that we can do with Gauss's theorem. So suppose now you have a surface that's a piece of a sphere. So here's a sphere. This is the sphere x squared plus y squared plus z squared equals 2. So it's a sphere of radius square root of 2. Square root of 2. And we're going to cut it off with z greater than or equal to 1. So this is our surface. We go up a distance of 1 and cut it off there. I'm not sure how this got so slanted, but it did. Fine, that's fine. So we cut it off here at z equals 1. This is the z-axis, and this is our surface. And we want it this time oriented in, just for a bit of something else. So oriented in. So there's our surface S. And our quest is to compute the flux over S of 2xy minus z squared, y minus y squared, negative z dot ds. That's what we want to do. Okay? So our first option is always to just compute it. So parameterize S, probably using spherical coordinates, because it's part of a sphere. So you would parameterize it with spherical coordinates, rho and theta and phi, because the thing always has rho equals square root of 2. You take theta going from 0 to 2 pi. You take phi going from 0 to pi over 4 to get you out to here. Fine. It would be good. You could do it. And then you translate this vector field into phi and theta using the transformation from spherical to Cartesian. But the Gauss, that looks like it probably will be a mess. So maybe we cannot do that. Or we could, but we could maybe try something else first. So option 2, use Gauss's theorem, closing off S. Because as it is, S is not closed. But if we have a closed surface, we can apply Gauss's theorem. So let's do it. So you could use any surface that has the same boundary as S. So the boundary of S is this curve here. So for example, we could add just the rest of the sphere. That would be okay. Or we could add, I don't know, another thing that looks exactly like this, but at the bottom. Or you could add some big thing on the outside so that this part ended up being just a little dent into the surface. Anything you want that has the same boundary. But we've been adding the simplest possible thing, which is a flat piece. So let's do that again here. So let's add a flat piece. So let's add the disk at height z equals 1. Here it is. Now, I left a space here because I wanted to say what its radius was. Can you figure out what its radius should be? So we can draw in a little right triangle here. We know that the radius of the sphere is square root of 2, and we went up here, a height z equals 1, and so this radius also needs to be 1. It's a 1, 1 square root of 2 right triangle, isosceles right triangle. So this is a unit disk at height z equals 1. So this is called S1, oriented. So do you think that the normal vectors for this pink S1 surface that we added should be up or down? Up. Why do you think up? Good? It's up?
I'm not sure. This seems it might be going to the surface or something. I don't know.
Yeah, anyone have an explanation? Yeah. Yeah, exactly. Yeah, the other ones, the normal vectors for S are pointed in to the solid interior. So you want the normal vectors for this pink surface that we used to close it off to also point in. So you want them to be oriented up. Okay. So oriented up with normal vector 0, 0, 1. Okay, great. So then the idea is that by Gauss's theorem, if your surface S is closed and oriented out, then the double integral over your surface of f dot ds equals the triple integral over the interior, the part that's inside your closed surface S, of divergence of f dv. Okay, so we have to make a couple of little changes to this. So if our closed surface is called S plus S1, because that's how we need, in order to make it closed, we have to have S and S1. And ours is actually not oriented out, it's oriented in. So Gauss's theorem says if it's oriented in, then you change the sign. So that's what we need. So that's what we'll do. Okay, so then we'll break this into its two parts. So the flux over S of f dot ds plus the flux over S1 of f dot ds is equal to the triple integral over E of divergence of f dv, and ours is negative because we have our surfaces oriented in. And so this part is the part that we want. So we can solve for that the double integral over S of f dot ds is the negative triple integral over E of divergence of f dv minus this part. So the double integral over S1 of this flux, f dot ds. Okay. Good. So now we just need to compute the parts. So let's compute this first part and the second part. So I'll just compute them positively and then we can subtract them later. So the triple integral over E of the divergence of f dv. Okay, so I think it was pretty clear, but I'll just make it, this is what I was calling f, this vector field. So let's compute its divergence. Okay, so derivative of the first term with respect to x. 2y. Whew, better record that. Might forget. Okay, triple integral over E of 2y. Okay, derivative of the middle stuff with respect to y. 1 minus 2y. So plus 1 minus 2y. Okay, derivative of the last bit with respect to z. Minus 1. Okay, so those are all our pieces. We want to do all that dv. 2y minus 2y, 1 minus 1. Hey, it all cancels out. Okay, so this is the triple integral over E of 0 dv, which is 0. Okay, so that tells us that the flux over the entire surface which we computed by doing the triple integral of the divergence over the interior, is 0. So the net flow through the whole surface is 0. Okay, well, now to see what the flow is through our surface, our white surface S, we'll just have to figure out what the flow was through our pink surface S1. So let's do that second part. So the double integral over S1, this part that we need, of f dot ds. Well, we could parameterize it and compute it. That would be fine. But maybe we can do this clever thing with the normal vector. So this is always f dot unit normal vector ds. So that is double integral over S1 of f something, 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 dot the normal vector. We figured out that our added surface S1 should be oriented up so that everything's oriented in. And so its unit normal vector is 0, 0, 1. So dot 0, 0, 1 ds. And I held off on copying this down just to see if I was going to be dotting it with any zeros. So I don't care what the first bit is. I don't care what the second bit is. And the last bit is negative z. Okay, so this is the double integral over S1 of something times 0 plus something times 0 plus negative z times 1. So negative z ds. Okay, and z. So now I could set this up in polar coordinates. It's just a disk. So I could set this up from r equals 0 to 1, theta equals 0 to 2 pi, r d theta. But this z, I guess it's not involved. It must be a constant. And I guess our whole disk S1 is up at a height z equals 1. So z equals 1 on S1. So this is the double integral over S1 of negative 1 ds, which is negative 1 times the area of S1. And we figured out that S1 was a unit disk, has radius 1. So its area is just pi. So this is negative pi. Okay. So this tells us that the flux through S1, oriented the way that we oriented it, is negative pi. So looking at our picture here, S1 is oriented up, and the answer we got was negative, which means that things are flowing down through our pink surface S1. And the net flow through the whole thing is 0. So if things are flowing like out of our pink surface S1, they must be flowing into S. So we expect, because the net flow through the whole thing is 0, anything that came out through the bottom must have gone in through the top. And in through the top, the normal vectors point in, so we should get a positive number. So I'm just saying why we should get something positive here in the end. Here we get negative of whatever we computed here, which was 0, minus the thing we computed, the flux of the other guy, which is negative pi. So this comes out to pi. So a positive thing. So pi worth of stuff flows in through the white surface at the top, and then just flows right out through the pink surface at the bottom. Yeah. Questions or ideas? Yeah.
So f there, since the divergence is 0, is a curl parameter. Is it a curl parameter?
Oh yeah, good point. So because the divergence of this vector field f is 0, it must be the curl of some other vector field. Yeah, good point. So it's a curl vector field, right? And we figured out that the curl vector field through any closed surface is 0. The surface integral of any curl vector field through a closed surface is 0 last time. So we shouldn't be surprised this came out to 0. Nice. Okay. Okay, so there are so many things that we can now integrate over. So I'll remind you that we have computed vector surface integrals directly in the past. We've just done it. We've also turned them into vector line integrals over the boundary using Stokes' theorem, and now we're turning them into scalar integrals over the solid region. But we can also compute them directly. So option 1 isn't always bad. Okay. Yeah. Like for instance, suppose the roles of these two surfaces had been switched, And I had given you this pink surface, S1, just this square, and said, hey, please compute the integral of this vector field over just this pink surface, S1. Probably you should just do it. You don't need to close it off into a closed surface. You could close it off by attaching the whole top of this cube, but that seems like overkill. Maybe just compute it directly. OK. So as the last example, let's do something that we need two pieces to close off. Like I am not, but most of you are wearing T-shirts. And so if you had a T-shirt surface, you have a hole for your head, a hole for each arm, and a hole for your waist. So in order to integrate over your T-shirt surface, you'd have to attach 4 pieces to close it off. You can think about what you would need for your pants or your socks. Yeah, or this dress, for that matter. So how about we have the surface? Our surface S is a hyperboloid, which is something we haven't seen for a while, but that's very sad because hyperboloids are so cool. So this S is part of the hyperboloid x squared plus y squared minus z squared equals 1. That's a squared. From z equals -2 to z equals 2. Oriented out. So this hyperboloid is centered on the z-axis. There's the z-axis going through it. Here's the origin right there, and the plane z equals 0. And then down here we have z equals -2. Okay, and up here we have z equals 2. And here's our surface, this beautiful hyperboloid, and it's oriented out. Okay, and suppose we want to compute some crazy vector surface integral over it. So we want to compute the double integral over S of y to the y times e to the cosine of sine z, comma, x to the 100, some crazy function of x and z, e to the z to the x to the z, and then x minus z squared, all of that dot ds. So we have this vector field that's flowing somehow through our hyperboloid surface, and we want to know positive, negative, 0, what's going on? Are we going to catch fish with this amazing fish catching design? Yes, perhaps. Maybe this is like one of those things that catches your fingers. Do you play with those toys, right? Yes, this could catch your fingers, but it might not be so good at catching fish. Okay, so option 1 always is to parameterize the surface and just compute it. But let's not do that. Let's use Gauss's theorem. So by Gauss's theorem, if you close S and orient it outward, then you can take the double integral over some surface of f dot ds, and that's equal to the triple integral over the interior of the divergence of f dv. Okay, but now we're going to have to close this off with 2 surfaces. So I haven't written the surface here yet because I'm going to say s plus s1 plus s2. I guess I'll just say that now. S plus s1 plus s2. So S1 will be this top surface. It could be anything. Again, it could be a spherical cap. It could be a paraboloid piece. But let's just use the simplest thing. This is the flat disk. And then down here, we'll put in S2. Again, just the flat disk. So let's have S1, where S1 is a disk at height z equals 2, oriented in some direction, and S2 is a disk at height z equals -2, oriented in some direction. Okay, so we have to figure out, what do you think? S1, should it be oriented up or down? Up. Yeah, up, because we want the whole closed surface S to be oriented the same way. The whole closed surface S1 plus S plus S2. And S is already oriented out. So these guys have to play together nicely. So S1 has to be oriented out, which in this case is up. So this is oriented up with normal vector 0, 0, 1. And then S2 is the disk down at z equals -2. It also needs to be oriented out. So in that case, it's oriented down. So it's oriented down. So its normal vector, its unit normal vector is 0, 0, -1. Okay? So now we have our setup, and let's compute. So Gauss's theorem says that if you integrate over this whole closed surface oriented out, it's equal to the scalar triple integral of the divergence. So I'll write this out again. It's so the double integral over S of f dot ds plus the double integral over S1 of f dot ds plus the double integral over S2 of f dot ds is equal to the scalar integral over the interior of divergence of f dv. So this thing that we want, double integral over s of f dot ds, we can get that by doing this right-hand side and subtracting off the flux over the two pieces. So the triple integral over E of the divergence of f dv minus the flux over S1 of f dot ds minus the flux over S2 of f dot ds. So these ones on the right are dot products. That one's just a multiplication. This one's also a dot product. Okay, so I'm writing that so that we know which pieces we have to compute and we can plug them back in later. So here's part 1, and then part 2, and then part 3. Okay, let's compute them all. So for part 1, the triple integral over E of the divergence of f dv. Okay, and now here E is the region enclosed by the closed surface. So I guess we better figure out what the divergence is. So this is a triple integral over E of the divergence. Okay, derivative of the first part with respect to x. 0, because there are no x's in it at all. Derivative of the middle part with respect to y. 0, and there are no y's in it at all. Derivative of the last part with respect to z. -2z. Okay, -2z dv. Okay, now so the last time I think we got 0, or a constant or something, 0. So we haven't had to integrate something like this. But now we do. So we have to set up a triple integral over that region. You are very good at this because in your web work you had some crazy surface that was some crazy solid that was kind of similar, like some sort of wooden pedestal thing, and you had to set up a triple integral over it. So you've done something like that. You could do it again if you needed to. No? You don't want to? No? Okay. So lucky for us, let's see, this function is so simple. Maybe we can figure out some way to deal with it. So this, in particular, this function -2z is odd with respect to z, meaning that if there's some way that it's symmetric with respect to z, the region, then it will come out to 0. So let's go over here and look at it. So if we look at the plane z equals 0, which cuts through the middle here, actually our solid is symmetric with respect to the plane z equals 0. Z equals 0 is like a mirror for it. So if you have a point anywhere up here, and you calculate the function -2z for this point, it will be equal and opposite to the value, when you calculate the function -2z for its buddy, its mirror buddy down here. So each point at the top has a mirror buddy at the bottom where the value of the function is equal and opposite. So they cancel out exactly. So the region E is symmetric across z equals 0, and the function -2z is odd with respect to z, so this is 0. So this comes out to 0 by symmetry. Okay. Okay, let's do one of the other parts. Okay, so for the second part, we want to do the double integral over S1 of f dot ds. Okay, always we could parameterize the surface and just do it, but since our normal vector is easy, it's just 0, 0, 1, I guess. Let's write it that way and see if we can get something to work out. So that's the integral over S1 of f dot n ds. So that's the double integral over S1 of our vector field dot our normal vector, and our normal vector for our surface S, which is the yellow surface at the top, was 0, 0, 1. We want to integrate that ds. Okay, so now I'll put the function in here. I waited on writing it down because I wanted to see if I was maybe dotting it with any zeros, and I am. So the first thing, I do not care what it is. The second thing, I do not care what it is. And the last thing is x minus z squared. Okay, let's take this dot product. So the dot product is just 0 plus 0 plus x minus z squared ds. Okay, so now we're going to have to integrate that over a disk. Maybe we can get something to work out nicely. Let's break this into two pieces. That's the integral over our disk S1 of x ds minus the integral, double integral over S1 our disk of z squared ds. Okay, how about this part? X. Again, x is an odd function. So if only our region S1 were symmetric with respect to x equals 0, we'd be good. But our thing, I'll draw it over here so you don't have to look so far. So here's our thing, S1. If the x-axis is coming out this way and the y-axis is going out this way, then x equals 0 is just the y-axis. So here's x equals 0, and indeed our region S is symmetric with respect to x equals 0. So S1 is symmetric across x equals 0, and x is odd with respect to x. That's a funny way of saying it, but if you had some x value here that was positive, let's see, it would have a buddy on the other side where the x value was negative, and so they'd be equal and opposite and they cancel each other out. So this first bit comes out to 0. And then how about z squared? So on S is up here at z equals 2. So z squared is just 4. So this is the double integral over S1 of 4 ds. So this is negative 4 times the area of S1. Okay, fair enough. So now we can just figure out, S1 is a disk, we can just figure out what its radius is, and then figure out this number. The other option, so that would be okay, and we'll maybe do that in a second. The other option is to say, you know what, I'm just going to leave this as the area of S1 and I'm going to do S2. So suppose we were doing S2. So I'll do part 3 here with the surface S2, which is this guy at the bottom. So here's what would change. This would be the double integral over S2. This would be the double integral over S2. S2 all along. This vector field is the same, but this would be a negative 1 instead of a positive 1 because the normal vector to S2 goes down. So this would be a negative 1. So we get a negative sign in front of this integral. So we get a negative sign in front of this integral and a plus here. Negative 0 is still 0. But for S2 then, we get plus 4 times the area of S2. So I didn't do the same calculation again because it would be the same, except for this negative sign. So in our calculation here, let's see. The integral of the first part, this triple integral, came out to 0. Then we subtract off -4 times the area of S1. So whatever that is, it's like negative something. And then we subtract off the same thing, but positive. So the blue thing. So this negative star and this positive star, whatever it is, cancel each other out. And we get 0. Because S1 and S2 have this same area. Yeah. If you had wanted to find the area of S1 and S2, it is not too hard. Because we can just calculate it. So we have our hyperbola here. It's a disk of some radius. What is this radius? We wish to know. Well, our hyperboloid is x squared plus y squared minus z squared equals 1. And this thing is up at height z equals 2, or down here at height z equals -2. Either way, x squared plus y squared, z squared is 4, so -4 equals 1. So x squared plus y squared equals 5. So square root of x squared plus y squared is √5, which is the radius of the thing. So we could figure out that the area of S1 is pi times √5 squared, or 5 pi. And same for the area of S2. Okay. So the idea of today was that if you want to calculate the flux over some surface, you could do it, but sometimes it's actually easier to slightly complicate your life by adding in extra surfaces to close it off using Gauss's theorem and then subtracting off what you added. So that's the idea. All right, thank you.